Hello student, how are you? I am Arun sir. Welcome to my channel Tuition Expert. Today in this class, I will teach you the radiation winds displacement law. Student, if you watch my video regularly and follow my class attentively, then I can assure you that you must crack the iitjee exam and NEET exam confidently with a good rank. Now let's start about the class. So today's topic is winds displacement law. Suppose hot body is placed. A hot body, follow this class. Suppose a hot body is placed in a surroundings. Hot body whose temperature is fixed. As the time increases, gradually the body becomes colder. We know that. Now at a particular temperature, it radiates all the wavelength whose all the wavelength, that is range of wavelength becomes infinity to 0. It radiates all the wavelengths. So the energy radiation is not constant at different wavelength. It is given that it is observed that energy radiation is different for different wavelength. So if we plot a graph between if we graph a spectral emissive power versus wavelength, then the graph will be this way. Graph will be this way. Now this is lambda, suppose m1, and this temperature is suppose T1. This temperature is T2. So the wavelength corresponding at maximum spectral emissive power lambda m2, and this is T3, and this becomes lambda m3. So if we draw the graph E lambda, that is E lambda is spectral emissive power versus lambda, we draw the different graph at different temperature. At a particular temperature, body radiates all the thermal energy whose wavelengths are different. Now at a particular temperature, the energy radiation will be different. Now if we draw a graph E lambda versus lambda, the graphs becomes this. That is from this graph it is observed that first thing is that as the temperature becomes more, that is if T1 is greater than T2 is greater than T3, then lambda m1 is less than lambda m2 is less than this. That is the wavelength. As the temperature gradually increase, the wavelength lambda m is the wavelength corresponding to the maximum spectral emissive power. So lambda m denotes the wavelength corresponding to the maximum spectral emissive power. So if we draw the graph lambda versus lambda, with lambda m, this wavelength correspond to the maximum spectral emissive power at this temperature T1, and this wavelength correspond to the maximum emissive spectral power, that is maximum energy, maximum intensity. Similarly, this is at temperature T3. So if T1 greater than T2, this temperature is more than this more. So this wavelength become less than this less than this. Now what is wind displacement law about this graph? Wind displacement law state that the lambda m into T So this become greater, this is more and this is short. So product of this and this and this is constant. That is lambda in general form, lambda into t equal to constant. This constant term is b, and b is called Wien's constant. Wien's constant, whose value is 2.89 into 10 to the power minus 3 meter Kelvin. Meter Kelvin, because this is meter, this is Kelvin, so unit is meter Kelvin. Lambda into t constant. So as temperature increases, the lambda m becomes shorter. That is, at higher temperature, maximum wavelength correspond to the maximum spectral wavelength becomes less. At higher temperature, lambda m becomes less. Product is constant. So this into this equal to this into this equal to this into this. From this P1 equal to this, product of this into this equal to constant. So from this formula we can solve the problem. We can solve the problem. At a particular temperature, the graph becomes this, and this wavelength correspond to the maximum spectral emissive power. Now, what is the graph? Graph states that as this temperature is gradually increased, then lambda shift to the left. So suppose another is now the maximum. Now the wavelength corresponding to the maximum spectral power is this. So this wavelength shift to the left. The first study is that the wavelength corresponding to the maximum spectral emissive power shift to the left, this side. So suppose this is T1, this is T2, T2 greater than T1. So this is lambda 2, lambda 1. So lambda m2 less than lambda m1. So first study is that if temperature increases, then the wavelength corresponding to the maximum spectral emissive power shift to the left. This is called, that's why this is called Wien's displacement law. The wavelength shift to the left if the temperature increases. The second study is that the area of this graph, this graphs is proportional to the t to the power 4, because we know emissive power equal to 0 to infinity e to the power lambda d lambda. Now this denotes the area of this graph, and E equal to formula is sigma t to the power 4. So area of this graph is proportional to the fourth power of the absolute temperature. Area of this graph is proportional to the t to the power 4, because emissive power equal to, we know this, and this represents the area of this graph. So this equal to emissive power, we know sigma t to the power 4. So area of this graph represents this. Now one question about this: E lambda versus lambda graph of one body at temperature T is this. Now area equal to A, and maximum, the wavelength correspond to the maximum spectral lambda m. Now if the temperature of the body becomes double, then what about the wavelength corresponding to the maximum spectral emissive power, and what become the area? So question is A dash equal to what and equal to what? This is the question. Now we know that the formula is lambda m into t equal to constant, Wien's displacement law. So lambda m into t equal to, here lambda m test into 2t, so tt cancel, so lambda m will be lambda m by 2. This is the one answer. one answer, and another answer of A dash. We know area is k to the power 4. A equal to k to the power 4. So here A dash equal to k into 2t whole to the power 4, which is equal to 16k to the power 4. 16k to the power 4. So 16 into A. 16 into A. So area becomes 16 times. Area becomes 16 times, and wavelength becomes half. Wavelength becomes half. This is the answer. Another thing is that E equal to 0 to infinity e to the power lambda d lambda. We know this equal to sigma t to the power 4. Now this is the emissive power. Now what is about the E lambda? E lambda into d lambda. Suppose this equal to lambda into t equal to constant. We know, so lambda equal to b by t. So if we put here d lambda, that is d lambda integration is lambda, so b by t equal to sigma t to the power 4. So E lambda equal to sigma by b whole to the power t to the power 5. So one result comes here, that spectral emissive power is proportional to the fifth power of temperature. E lambda is proportional to the t to the power 5. E lambda is proportional to the t to the power 5. This result comes. One problem related to one displacement law is that, suppose here given that the spectral energy distribution of the sun has a maximum at 4753 angstrom. If the temperature of the sun is 6050, what is the temperature of a star for which this maximum is at 9506 angstrom? So you study the question first. The spectral energy distribution of the sun has a maximum at this. If the temperature of the sun is this, what is the temperature of a star for which this maximum is at 9507? So for convenience, I draw the picture. Suppose this is a star. This is a sun. This is a sun whose temperature is given 6050 Kelvin, and the maximum wavelength corresponding now the energy maximum energy occurs at this wavelength. Maximum energy, that is lambda, maximum energy this wavelength corresponds to the maximum energy. So this is 4753 angstrom, and for another planet or star whose temperature is to give in, and the wavelength for the star is 9506. What is the temperature of the body? So here we use the Wind displacement law, which is lambda m into t equal to constant, that is lambda m1 t1 equal to lambda m2 t2. We use this. Now this temperature should always at Kelvin scale. If degree centigrade, if temperature is given at centigrade scale, then we have to convert in Kelvin scale, because this temperature is always in Kelvin scale. So here we put 4753 into T1 equal to this into T2. So from this we get the T2. Another problem related to Wind's displacement law is that if the filament of a 100-watt bulb has an area this and behaves as a perfect black body, find the wavelength corresponding to the maximum in its energy distribution, given that Stephen's constant is this, and also Wind's constant is this. So suppose a bulb, solution is that. Study the question. if the filament of a 100-watt bulb has an area of this, area is this, and behaves as a perfect black body, find the wavelength corresponding to the maximum in its energy distribution, given that Stephen constant is this and Wein's constant is this. Stephen, so suppose this is a bulb, and it has the area is given 0.25 centimeter square, means 0.25 into 10 to the power minus 4 meter square. This is the area. Now we know what is power. Power equal to energy by time. What is energy? Energy equal to total energy, that is Q by T, equal to what? Q equal to perfect black body. So Q equal to sigma T to the power 4. Sigma T to the power 4. Sigma T to the power 4 per second. So this power is watt, means joule per second. Time is 1, and sigma T to the power 4 into total area A. So this is the energy radiation, sigma to the power 4 into A. Now P equal to what? P equal to given 100. So 100 equal to sigma 5.67 into T to the power 4 into area. We get area equal to this 0.25 into 10 to the power minus 4. So from this we get T to the power 4. T to the power 4 equal to 100 divided by 5.67 into 10 to the power minus 12, 0.25. So this becomes, now minus 12 minus 2 minus 40. So 10q into 10 to the power 14 divided by 25 into 5.67. So this becomes 10 to the power suppose to 10 to the power 16, 10 to the power 14 3 17 16 16 into 10 25 into 5.67. So if we calculate this becomes the value T equal to this to the power 4, this to the power 1/4, T equal to this. So if we calculate one by 4, so this becomes, suppose a value is, we get 2898. This value will be given, suppose this value becomes this, say this value is this. The question comes in such a way that you can calculate the fourth power. So suppose this value is this. Now we get the temperature of the bulb. Now what is the value of wavelength? To find the wavelength, now we use lambda m into T equal to constant, whose value is this. So we get the T. So now lambda m equal to this by T. T is given. T we get this value. This wavelength is, unit will be meter. Student, this is the end of the class today. To get more important problem related to JEE Main and NEET, watch my another video. Now see you again in next video. Okay, tata, bye bye.